Hey guys, and welcome back to another YouTube video. In this video, I'm going to be teaching you how to create an autoencoder in Python. Now, we are going to be creating a very simple autoencoder. It's going to be like a very basic autoencoder just so that I can familiarize you with the concepts of what autoencoders are and how to go on and create them. So first off, we have to look at what really an autoencoder is. So I have, as you all might be knowing if you have watched my previous videos, you know that I'm kind of in the process of writing these notes for neural networks, and I have all of this on GitHub, so you can check it out, if you wanna. And over here, as you can see, I have added another chapter on GANs and autoencoders. Actually, I've added a bunch of chapters. I also added one on attention mechanisms. I'll be covering that in a future video. But for now, let's just look at these. So what are GANs and autoencoders? So first off, we have to look at what really an autoencoder is, because that's really the core question. So what an autoencoder is it learns to take a bunch of inputs. So usually it's going to be images, and it learns to basically copy them and produce an output. So let's say if you use the MNIST digit data set, then it will take in the digits, so like the 5, 7, 8, whatever, and it will output a digit that has been reconstructed by the neural network. Now, I know what some of you might say, well, that's kind of stupid. Why would you even use a neural network to basically produce the same thing? I mean, isn't that just illogical? Now, now the thing is, for the use case that I am saying, yeah, it pretty much sounds illogical. But there are a bunch of other use cases that autoencoders have. For example, denoising, and you can also create what is known as a variational autoencoder. Now, variational autoencoder is a little different from your traditional autoencoder that we are going to be covering in this video. It's a little more complex also, and I'll cover that in a future video. Basically because it's a pretty complex topic. Like, it is different from autoencoders a little bit, and it is also a little bit where I want to get into the math, so I won't be covering it in this video. So for this video, just assume that autoencoders are useful, and if you look up on Google, you will see that there are a lot of use cases for autoencoders. So what is an autoencoder? It learns to copy the inputs into the outputs. Now, there are a bunch of things that I would kind of want you to know about an autoencoder, which is the first thing is that it is an unsupervised training algorithm, learning algorithm. What that means is that we aren't exactly giving it any labels. We are just feeding the images. So it's unsupervised. So it's not like a traditional image classification neural network, because that's supervised. Then typically, one thing that you really need to keep in mind is that an autoencoder looks something like this. Now, what this means is that the number of nodes in your input layer have to be equal to the number of nodes in your output layer. The reason is that when you are producing your output image, you want it to be of the same resolution of the input image. Just a second, guys, I'll be back. So that's really what you need to keep in mind, is that you want the output of your autoencoder to be of the same dimensions, because otherwise it doesn't make any sense. So the way an autoencoder is created is it's got some couple of things. It is made up of two parts. It's the encoder and the decoder. And another thing to keep in mind is there's also this another thing which is known as the code, also known as the coding layer, or whatever you want to call it. And what this means is that basically what the autoencoder will do in here is it will take the inputs and it will transform it into some lower dimensional representation of the inputs. Then those outputs of the encoder will be fed to the decoder, and it will try to take those lower dimensional inputs and construct an output from that. So it's like big to small and back to your original thing. So now let me actually show you one of the use cases of autoencoders. So one of the major use cases for autoencoders is denoising autoencoders. So if you have like a very bad image, so let's say that you have a video from the 1900s, like and the image quality is very bad, or the video quality is very bad, And let's say you are a police inspector and you want to identify someone from that clip. Obviously, I'm pretty, the chances of that person being alive, and if they are in the 1950s, isn't going to be that high, but just saying. So basically, since the image quality won't be that great, you won't be able to identify the person. So what you'll do is you will just take the picture of that person and you will feed it into your autoencoder. And you would have already trained your autoencoder on how to take like a noisy image and convert it into something that you can actually see, and you will actually get a upscaled kind of a very good quality image. So that's really why autoencoders are pretty useful. So yeah, so let's actually dive into this. So all you need to do is just open up your terminal, whatever it is, and we can just cd to whatever directory you want to make your project in. If you don't have any, now I'll be using TensorFlow for this project. You can use PyTorch if you want, like if you want to, and yeah, so it's up to you, whatever it is that you want to use. Now I'm just gonna create a new directory. I'm gonna be doing this on the fashion MNIST dataset, so I'm just gonna say fashion MNIST autoencoder, and then I'm just gonna cd to that directory. Oops. Alright, and now I can just open up a Jupyter notebook, a blank Jupyter notebook, so that we can actually get started working on this. So I spent a little bit of time explaining what autoencoders really were. So now I'm gonna show you what they really are in practice, so you can get a bit of a better understanding on what they are. Because right now it was all just pretty theoretical, nothing was like applied. And I usually like to understand things by applying them. So, all right, but we're gonna have to wait for this Jupyter notebook to open up. Why is it taking so long? It's usually super quick. Like it's very quick. Why is it taking so long this time? Is it lagging? I doubt. Let's try to open it up again. Bro, why is it taking so long? Alright, there we go. Alright, so now we can get started. So I'm just gonna go ahead and create a new Python file. There we go. And I'm just gonna call it main. You can call it anything you want. So let's just go ahead and first import the libraries that we're gonna be using. So first off, we are obviously gonna be using TensorFlow. So import TensorFlow STF. From TensorFlow import keras, import num as in p, and we're also gonna need matplotlib just to display our stuff. Alright, so now we can actually load in our dataset. So load in the dataset. So loading in the dataset, since we are using a keras dataset, you can use a custom dataset if you want. It is very simple to load in a dataset of your choice. You can just make use of like stuff that TensorFlow is already keras already provides. So you can just use like the image data generator and flow from directory to easily load in your data. I already have a bunch of like neural network videos where I'm doing the same thing, so you can just check that out if you want. But just for this video, since I want to keep it simple, I'm just going to be using this dataset. So I'm just going to call it data is equals to keras.datasets, and you can use any one you want. Now I would recommend that you use either the fashion MNIST dataset or the MNIST digit dataset. The reason why I say that is because both of those datasets are very simple for a computer to understand and process and stuff. If you use the Cypher 10 or the Cypher 100 dataset, what's going to end up happening is that your images are going to be RGB, and so you won't be able to get very good results using a traditional MLP type of autoencoder or a dense autoencoder that uses dense layers. and instead of that you're going to be using what is known as a convolutional autoencoder, which is a little more complex to create and even fine tune and tweak. So I wouldn't recommend that you use the Cypher 10 right now, but once you're comfortable with how autoencoders work, you can move your on with some more complex data. So we can just go ahead and split our load in our data. So X train, Y train. So we can just do that, and we can just call the data.load data function on that. There you go. So that's all we need to do, and this should actually load in our dataset. So now I'm just gonna show you what our dataset really looks like, just so you can get a good idea. So we can just get the X train 0, and what I'm gonna do is I'm just gonna add a CMap of binary, so I can just get it like in a black and white format. There we go. So as you can see, we have a boot, and if I do 1, then it's a t-shirt. 10, then it's some whatever this is, it's a t-shirt, but I don't know, whatever, as you can see. All right, so now let's go ahead and normalize the training data. So normalize the training data. What I mean by normalizing is just divide the X train and the X test by 255, so that we can, because RGB ranges from 0 to 255, and if you divide your X train and Y train by 255 each, what's going to end up happening is you're going to have a bunch of values that lie between 0 and 1, and that's what neural networks are very good at predicting and even looking at. So that's what you want to do. So we're going to take the X train, and we can take a and just divide it by 255. Just do that same thing with the X test. That's all you need to do. So now if I just have to show you something, if you get the shape of the data, this is something that you really need to keep in mind. As you can see that the image of our that we are using here is a 28 by 28 image. Keep this in mind. This is a pretty important thing to keep in mind. So the first, now we can actually get started creating the encoder. So basically the way we create this is we actually the way we have like a autoencoder is we have an encoder, then we have a decoder, and then we have a model which is just equal to the encoder plus the decoder, and all of these are going to be sequential. All of these are going to be sequential in nature. So it isn't anything like a DC GAN where you won't be having a sequential model. So this is how what it looks like. So basically when you are compiling and fitting the stuff, all of this will be applied to your model, not the encoder and decoder. It's just going to be applied to the model. So this is really what an autoencoder architecture really looks like. Autoencoder architecture. I'm pretty sure I didn't spell it correctly, but yeah. So this is really how this works. It's pretty simple. Also, how can I do a line break on this? Is it that? Hopefully. No, that is not correct. What? So we can just do a slash n, backslash n. No, even that's wrong. But whatever. You know what? I'm just gonna get rid of this. Alright. Yeah, there we go. So let's go ahead and create out the encoder. So we can say encoder is equals to the keras dot sequential there you go. And first off, we're gonna pass in a flatten layer just to take our data and put it in like one long thing. And we can pass in our input shape, which is gonna be in this case it's gonna be 28 by 28, since we already know that. Don't pass in anything else or you'll just get an error unless you are using a different data set. So now we can just pass in a dense layer. You can have anything in here, it's up to you. I'm just gonna have like a 100 node dense layer with an activation of value, and then I'm just gonna add another dense layer with around 30 nodes and an another activation of value. So that's really it for the encoder. Now we can go ahead and create the decoder. So the decoder is just gonna be like the encoder, like 90%, and this is gonna be a little different. So the way this works is that if you see this is gonna be your coding dimension, so 30, and then basically what we do is we take the data from the coding dimension that we have over here, and then we just increase the dimensions to whatever we had originally. So in this case, you can see the way this works is it kind of goes big to small and then small to big. So it's not like small then the output and then like that. So what this will be is that the tens layer in here will actually be having 30 nodes with an activation of value. Now just keep in mind that the activation that the number of nodes of this dense layer and this dense layer should match, and what I'm doing now also should match. So now if I do a keras layers dense, I think I need to do 100 with activation. Actually, I don't even think I need to do 100. I think I can. Let me check. Just a second. I'll just quickly have a look at it because I've already written this code, and I also am currently reading about autoencoders in a book. So I'm just gonna really quickly have a look so that I don't have to run this code again and again. So yeah. Oh yeah, okay. So all we really needed is we don't even need to pass in the 30 in this case, since we already have specified 30 as the coding dimension. So we can literally just go and have 100 in here, and all we really need to do is we just need to specify an input shape parameter to this dense layer, and if we do that then it'll just work. So let me show you. So we can just pass in a input shape parameter to this of 30, and then we can just have a dense layer, and I'm just gonna say, since it's 28 by 28, I'm just gonna say 28 28. So this is gonna have the number of nodes equal to the square of 28, so that's gonna be 784. And so now what we can do is we can just kind of create the final like output. We currently already have the output after this. Actually, this is going to be a softmax since we got a probability, but since this is a 784 and not a 28 by 28, we can just add a reshape layer which basically reshapes data. So you can just do that, and if you do that then that should reshape the data. But now we still just have the encoder and decoder in place, so now we can actually construct the model. So the model is going to be as sequential, and it's just going to be equal to the encoder and the decoder. So you can just say encoder and the decoder. That's all you really need to do. So that's your model in place. So now we can just do what we always do, just compile and fit the model and just see the predictions. You really just don't need to do anything else. Now the losses that we use in this case are usually going to be binary cross entropy or the mean square error loss. You'll have to use one depending upon your use case. Here our use case is to use a binary cross entropy, so that is the one I am using. So now we can just go ahead and fit the model on, I don't know, 5 epochs. You can use again any number of epochs that you want. It really depends on your processing time, speed, stuff like that. If you have a very fast machine, then you don't even need to use this data set. You can just use like a very different complex data set, and it will still work. On the other hand, if you're using a super slow machine, then again you would not want to use this. And as you can see, it's taking a little bit of time for it to process my thing. Also, I think I can use stochastic gradient descent on the other hand, and actually instead of even using ReLU, I'm just gonna use CellU, because the book that I read, which is hands-on machine learning with scikit-learn, keras, and tensorflow, and I'm just gonna show it to you. If you want to look at it or purchase it or something, this is the one I basically refer to. It's pretty much something that almost everyone has who is interested in like neural nets and machine learning. uh, I checked and they really like using CellU. I don't know. I know that cell you can get rid of the dying relu problem, but I don't know how much it's gonna help us in this case. But I'm still gonna use it. Other than that, I'm just gonna have one epoch over here because it's taking me a little bit of time to do this training, and I know I could make this a lot faster by just training this off camera. Because currently what's happening is, since I'm recording and since I have a bunch of stuff open right now, it's not able to really train at a full speed. So that's really the reason why we are getting the slow training and stuff. But I mean, I can't really do anything about it at this point, so I'm just not gonna do anything. Well, with the stochastic gradient descent, I actually didn't get a good loss. I actually got a bad one, but that's okay. So now you can just get the predictions. You can tweak this model however you want. So we can just call our model predict on the X test. And we can just do a M show of the predictions. There we go. That's really all you need to do. Okay, that's pretty bad. Oops, this is not correct. Also, I think I should just put in this thing in another cell. And I'm also just gonna say okay, now that's not that good of a prediction. It's really just not even able to predict anything. It's just doing random noise. Okay, I think one thing I can really just do to maybe improve this is just add a steps per epoch parameter. And I mean, if we are trying, I'm just gonna use every single optimizer that I can. I mean, okay, the model really isn't improving that much. Uh, so I don't understand exactly why it's not improving that much. Which is what kind of makes me a little. I don't understand. I'm literally doing everything correct. Maybe we don't need to normalize it. I don't know. Because I'm pretty sure we have to normalize the data every time. Because you can't have a neural network without that. But I'm gonna try that. Maybe we don't need to normalize the data. Because I mean, I've trained a lot of neural nets, even autoencoders on this stuff. And there we go. As I told you, you always need to normalize the data. You can't have any neural network without normalizing the data correctly. Yeah. So I have to normalize it. That's correct. Maybe you can just use add. Maybe we can just use MSE on this one. I have to be making some kind of a mistake because I really don't think this is a good model. I mean, sure, you can tweak it all you want, but I don't think it's a good model. It's a pretty not so great model because it's just able to generate noise. It's not able to generate an actual prediction. Like, I don't even see how this resembles a shoe. it's just got it like completely wrong, so it really doesn't make a lot of sense. I mean, if I want, I can run this again, but it's not really gonna make any difference. Yeah, so this time you actually get something that kind of resembles a boot. And maybe, if we increase the number of epochs to something, we might get something that resembles this a little more. But I mean, it's pretty not that great. It's just not that great. But I mean, what else can I do? So I actually have trained a model very similar to this, as a prep for this video, and we can just look at the results that that model produced. I think I might have not saved the results when I kind of closed up my Google Colab. I was trying this out on the Google Colab before. So yeah. So we are still on the fifth epoch. It should take a little bit of time to trade. I'm guessing, if everything works out, but we should reach a good loss. But given the fact that there is no reduction in the loss, I don't think it's gonna be that great. Alright, so this was the one that I kind of prepped for. So this is where I. So let's have a look at this model. Plus, we'll get access to a GPU on this one, so that's pretty cool. And I might not be able to run both of these side by side. It will get a little heavy, so I might just stop training this one or run that one after I train this one. So just as I suspected, as you can see, there really isn't any exponential convergence to a minima, so that's why it's really not able to get us a good accuracy on this one. So we can just use this model. It's a little different. As you can see, I have played with the hyperparameters a bit. For some reason, the predictions on this one are just a lot better. The loss itself is a lot better. And if we use these hyperparameters, and these are the metrics that we are getting. Let me see if we are using a GPU, because if we are not, I want to use that one. So I'm just gonna train all of this just so that we can get a feel. So yeah, again, we're not gonna get any better predictions. It's gonna be a pretty bad model. Okay, so as you can see now, it's actually resembling a boot much more, and it actually looks close to a boot. That's good. So again, that's really just how much I can go to. I don't think I can get you a much better model. Again, you can train this a lot more. As you can see, when I'm using these hyperparameters, I'm getting a much better accuracy. So you can just use these hyperparameters. The one we are using are pretty bad, so don't use the one that, again, this book is not perfect. They are using Celio and Sigmoid, and that just did not work out. As you can see, those predictions are clearly a lot more better than the one we are having. So we just use this one, because I mean, look at the loss. It's pretty good. So that's why. But again, it is all up to you. You can tweak this model however you want. You can add more dense layers if you want. Just keep one thing in mind, is that whenever you add anything over here, you wanna add something over here, because if you don't, then it's just not gonna work. So just keep that one thing in mind. As you can see, it is a pretty good model, and it is also training very quickly. Main reason being, we are on a GPU. So that's one of the cool things about Google Colab. Alright, so we have finished training, and so now we can get a look at the predictions that we are getting. I'm gonna have this code up, so you guys can check this out. As you can see, the predictions are pretty good. I mean, this one you can't even differentiate which is like which. It is a little different over here, but I mean, you can't even differentiate that. And over here it kind of screwed up. It shouldn't have created that. This one, it kind of got a little blurry. So basically, if I look at this, the one thing that I can conclude is that it's not very good at generating like white pixels. As you can see, it makes them a little gray and stuff. But I mean, in comparison to our last model, the one that we have uh, on this one, I'm gonna just use the ones that the hyperparameters that we are using here, just so that we can mimic that same accuracy. Not exactly mimic, I mean, there's gonna be a little bit of, it's just also on a little bit of luck that you are able to get those high accuracies. The reason why I see that is because it's on the initializations that you get. If the weights and biases are initialized very nicely, then it's gonna be good. So there you go. As you can see, if you use these hyperparameters, it's really good. So just use this model. It's a pretty good one. And yeah, that's it for this video. I hope you enjoyed it. This was an introduction to autoencoders, and just we created a very basic autoencoder. And as you saw, they do give you like major uh, differences in outcomes based on the hyperparameter. So you should be very careful when you initialize them, because I was like pretty sure that I had used the same ones that I had used over here in this notebook initially, and so I just didn't change anything else. But turns out, just by changing a couple of things here and there, you can really change your output. So let's just do one last training, and then we can end the video. So just by adding a steps per epoch, we can get this training done a little faster. You can even save the model if you want, and kind of so you don't need to train it every time. But I'm not gonna do that, since the autoencoder that we have created here is a pretty, I don't want to say it, but it's just the truth. It's pretty useless. You probably want to add some functionality like a denoising autoencoder, something like that. That would be a cool thing to make, a denoising autoencoder, because it actually has a pretty good use case. But I mean, yeah, that's pretty good. And really, the way you create a denoising autoencoder is very simple. All you really need to do is just add a dropout before you do anything to your encoder. So basically, over here, before you even add your dense layer, you can just add a dropout. Basically, because what a dropout does is it basically deactivates a couple of neurons, depending on how many you specify, like point 0.1, point 0.2, point 0.3. It will just deactivate them for some time, uh, for that iteration, and that will kind of add noise and stuff, and then your autoencoder will be able to denoise it, and it's a pretty good thing. So I'm also gonna show that, because I want you guys to really see stuff. You see one use case of what autoencoders are, before I end up with this video, because otherwise I want to develop an intuition. I don't just want you guys to like do stuff for the sake of it. So that's why. All right, so we're doing it as, again, it's nothing. All you really need to do is just do this: keras dot layers dot drop out. Now you can specify any dropout. I'm gonna just do point 0.3. Point 0.3 means 30%. So don't go ahead and do something like point 0.9 or 0.95, because that will just, you will need a much better autoencoder for that. The reason why I'm just doing point 0.3 is so we can have like a very basic thing. And you will see that even with these noisy images, the first thing that you notice is the fact that our loss goes up. And that's just common sense. I mean, by adding the dropout, you're making your images more noisy, therefore the reconstructions of the images are going to be much harder. And also, you have fewer neurons in process working, so that's why. But I mean, even though that's the case, you can see that a model converges really quickly, and we almost end up with the same loss. It's still about 10 more, but I mean, that's okay. So as you can see here, it was actually given very noisy images, but I mean it still managed to do it. So yeah, but I wanna try to do something like, if you want, you can just use something like this. You can just do something like tf dot random dot normal, and you can just go and do some random noise. So you can just create like a 20 by 20 random noise like this one. Let me show you what that looks like. Just do that. So what you can do is you can have this random noise. Let me make a Gaussian noise, so it follows a bell curve. If you want to know that, you can just look up a Gaussian distribution on Google. Basically what we are doing is we are generating noise based on this, and once we have this noise, you can just add this noise to your data. So if you do that, then that should work out. And really, because right now